There are worlds where metal falls from the sky as rain. Planets where winds scream across the surface at speeds that would shred diamond. Places where gravity would flatten you into a smear before you even realized what was happening. These aren't science fiction nightmares. They're real planets we've discovered orbiting distant stars, each one pushing the boundaries of what we thought was physically possible. And the more we find, the stranger they become. Start with HD 189733b, a planet that looks deceptively beautiful from a distance. Point your telescope at this world and you'll see a brilliant azure sphere, almost Earth-like in its color. Get closer and you realize this blue comes from something far darker than water. The atmosphere contains silicate particles. Tiny fragments of glass suspended in clouds that circle the planet at 7,000 kilometers per hour. The winds don't just blow. They obliterate. Anything caught in those storms would be sandblasted into oblivion by microscopic shards moving faster than bullets. But the glass rain is just the opening act. The temperature on the day side reaches over 1,000 degrees Celsius, hot enough to vaporize most metals. The planet orbits so close to its star that it's tidally locked, one face eternally scorched while the other freezes in permanent darkness. Between these extremes, the temperature differential drives those apocalyptic winds, creating a hellscape that makes every terrestrial storm look like a gentle breeze. What's remarkable isn't just that this planet exists. It's that we can measure these conditions from over 600 light-years away. We've mapped its wind patterns, analyzed its atmospheric composition, even detected the silicate particles that give it that false ocean blue. The technology required to extract this information from faint starlight is staggering. Yet HD 189733b isn't even the hottest planet we've found. KLT 9b holds that record, and it's not close. This world orbits a star considerably hotter than our Sun, and it does so at a distance that makes Mercury look distant. The result is a planet with a dayside temperature exceeding 4,300 degrees Celsius. That's hotter than many small stars. The planet is literally being vaporized by its own heat, losing its atmosphere into space in a constant stream of escaping gas. At these temperatures, molecules don't survive. Water, carbon dioxide, even molecular hydrogen break apart into individual atoms. The atmosphere of KLT 9b contains gaseous iron and titanium, elements that exist as solid metals on Earth but here float freely as vapor. The planet glows from its own heat, emitting more light than some red dwarf stars. But temperature extremes cut both ways. While KLT 9b bakes at stellar temperatures, other worlds freeze in darkness that makes Antarctica look tropical. OGLE 2005 BLG Free 90LB exists in the outer reaches of its solar system, so far from its dim red dwarf star that it receives almost no heat. Surface temperatures drop to -220 degrees Celsius, cold enough to freeze carbon dioxide into dry ice and turn nitrogen into liquid. This isn't just cold. This is the kind of cold where the laws of chemistry change, where gases become solids and the concept of weather loses all meaning. The planet is 5 times Earth's mass, likely rocky beneath a frozen shell of ice and solid gases. If you could somehow stand on its surface, the sky would be black even at midday. The star would appear as little more than a bright point, offering no warmth, barely any light. In that darkness, the only movement would be your own heat dissipating into the void. These temperature extremes reveal something crucial about planetary formation. The habitable zone we talk about, that Goldilocks region where water can exist as liquid, is vanishingly small compared to the range of distances where planets actually form. Most worlds in the universe exist in conditions incompatible with life as we know it, baked or frozen beyond recognition. Then there are the planets that break our understanding through sheer gravitational absurdity. Trace 4b has a density comparable to cork. This gas giant is nearly twice the size of Jupiter but weighs less than you'd expect, creating a world so bloated and diffuse that it challenges our models of how planets can even hold themselves together. The gravity at its cloud tops is weak, the atmosphere extended far into space, the entire structure seemingly on the verge of dissipating. Scientists initially struggled to explain how Trace 4b maintains its inflated state. The leading theory involves tidal heating, where gravitational interactions with its star constantly flex and squeeze the planet's interior, generating enough energy to keep it puffed up like a cosmic balloon. But the math is tight. This planet exists right at the edge of what should be possible. On the opposite end sits PSR J1719-1438b, a planet that shouldn't exist at all. This world orbits a pulsar, the collapsed core of a dead star spinning hundreds of times per second. The planet itself is thought to be the remnant of a white dwarf star, compressed by the pulsar's gravity into something stranger than fiction. The density is incomprehensible. The entire planet, larger than Jupiter in mass, has been crushed into a sphere about the size of Jupiter but with density approaching that of diamond. In fact, scientists believe much of the planet has crystallized under the extreme pressure into actual carbon crystal. A planet-sized diamond orbiting the corpse of a star, bathed in radiation that would sterilize anything foolish enough to approach. The pulsar's gravity is so intense that it warps spacetime around it, bending light and stretching the very fabric of reality. Standing on PSR J1719-1438b, if you could somehow survive the radiation and gravitational stress, time itself would flow differently than it does on Earth. Minutes for you would be hours for someone far from the pulsar's influence. This brings us to one of the most disturbing categories of extreme planets. The worlds that orbit so close to their stars they're being actively destroyed. Kepler 70b circles its host star once every 5.76 hours. Think about that. A year on this planet is shorter than a work shift. The orbital velocity is staggering, the planet screaming through space at hundreds of kilometers per second just to avoid falling into the star. At this distance, the stellar radiation is overwhelming. The surface temperature exceeds 7,000 degrees Celsius, hot enough to vaporize rock. The planet is thought to be the exposed core of a former gas giant, stripped of its outer layers by the star's heat. What remains is a ball of molten iron and rock, glowing white-hot, slowly evaporating into space. But perhaps no planet better demonstrates the universe's capacity for creating nightmares than HD 80606b. This world follows one of the most extreme orbits ever discovered. It's not circular like Earth's path around the Sun. It's wildly elliptical, swinging from a relatively comfortable distance out to the equivalent of Earth's orbit, then plunging inward to skim just above its star's surface. When HD 80606b reaches its closest approach, the temperature spikes by more than 700 degrees Celsius in just 6 hours. The atmosphere doesn't just heat up. It explodes. Supersonic shock waves race around the planet as one hemisphere suddenly receives 1,000 times more radiation than it did hours before. Storms larger than Jupiter erupt from nowhere. The entire climate system collapses and reforms in real time. Then the planet swings back out into the cold, and the process reverses. The atmosphere freezes, contracts, settles into an uneasy calm. For a brief period, conditions almost stabilize. Then the orbital mechanics drag it back toward the star, and the cycle begins again. Any hypothetical moon orbiting HD 80606b would experience tidal forces strong enough to literally pull it apart. The gravity differential between the near side and far side of such a moon would exceed the structural strength of rock. It would disintegrate, forming a ring of debris that would gradually rain down onto the planet below. These aren't outliers. We've found hundreds of planets in similarly extreme configurations. Hot Jupiters orbiting closer to their stars than Mercury orbits our Sun. Super-Earths with surface gravity that would crush human bones. Ice giants wandering through interstellar space, ejected from their home systems by gravitational chaos. Each discovery forces us to expand our definition of what's possible. The universe isn't just stranger than we imagine. It's stranger than we can imagine, constantly presenting us with conditions that violate our intuitions about how reality should work. But temperature, gravity, and orbital mechanics are just the beginning. There are planets where the very substance of the world defies explanation, where matter exists in states we can barely comprehend. Places where the rules we take for granted simply don't apply. And those worlds reveal something even more unsettling about the cosmos we inhabit. Consider the Diamond Planet. 55 Cancri e, a world 8 times Earth's mass, orbiting a star 40 light-years away. Initial observations suggested something impossible. The density readings, the way it reflected light, the thermal signatures, all pointed to a composition that shouldn't exist at planetary scale. The surface pressure on 55 Cancri e exceeds anything in our solar system. Under these conditions, carbon doesn't form graphite or coal. It crystallizes into diamond. Not scattered gems buried in rock, but layers kilometers thick of pure crystalline carbon. The entire mantle could be diamond, wrapped around a core of exotic materials we can only theorize about. Temperature readings show the day side reaches nearly 2400 degrees Celsius. Hot enough that the surface might not be solid at all, but a sea of liquid carbon with floating icebergs of diamond. At night, when temperatures drop, that ocean could freeze solid, creating tides of crystallization that sweep across the planet's face. The physics are borderline absurd. Diamond has the highest thermal conductivity of any natural material. Heat should distribute evenly across such a world. Yet 55 Cancri e shows massive temperature variations between its day and night sides, suggesting atmospheric dynamics we don't understand, or perhaps a composition more complex than pure diamond. Some models propose the surface is covered in a thick haze of silicon carbide and silicates, with the diamond layers buried beneath. Others suggest the planet is losing mass, that the intense stellar radiation is slowly stripping away its outer layers, creating a glittering tail of vaporized carbon that streams behind it through space. Then there's the question of formation. How does a diamond planet even come to exist? The most likely explanation involves a white dwarf, the collapsed remnant of a dead star. If a carbon-rich planet orbited close enough, the white dwarf's intense radiation could have stripped away the lighter elements, hydrogen, helium, leaving only the heavy carbon core behind. Over billions of years, pressure and heat transformed that core into the crystalline structure we observe today. But 55 Cancri e orbits a normal star, not a white dwarf. Which means either our formation theory is incomplete, or this planet has a history we haven't uncovered yet. Perhaps it formed elsewhere and migrated inward. Perhaps it's the remnant of something larger, destroyed by forces we can only guess at. Move beyond diamonds, and you find planets where matter exists in states that sound like science fiction. PSR J1719-1438b orbits a pulsar, the rapidly spinning corpse of a massive star. The planet itself appears to be crystalline carbon, similar to 55 Cancri e, but with a crucial difference. The intense gravitational field of the pulsar has compressed the carbon into a state that might be closer to a single giant diamond than a planet with diamond layers. The entire world, roughly the size of Jupiter but far denser, could be one enormous crystal lattice, atoms locked into perfect geometric arrangements by pressure that exceeds anything possible in normal stellar systems. the surface gravity would be lethal. Time itself would run slower near such a massive, compact object, the effects of general relativity becoming noticeable even to hypothetical observers. Then you encounter the lava planets. Worlds like K2-141b, where the entire surface is an ocean of molten rock hundreds of kilometers deep. The day-side temperature exceeds 3,000 degrees Celsius. Silicate rock doesn't just melt, it vaporizes, creating an atmosphere of rock vapor that rises into the sky, condenses into clouds, then rains back down as liquid stone. Imagine standing on the night side of K2-141b, if such a thing were possible without instantly dying. The ground beneath you would be solid rock, cooled by the permanent darkness. Above, the sky would be dark, but not empty. You'd see the glow from the day side, a permanent sunset that never moves, marking the boundary between frozen stone and vaporized crust. Wind speeds on these worlds can exceed 5,000 kilometers per hour. The temperature differential between day and night drives atmospheric circulation so violent it defies comparison. These aren't weather patterns. They're continuous planetary scale explosions, shock waves propagating through vapor that was solid rock just hours ago. The supersonic winds carry heat from the day side to the night side, but not efficiently enough to equalize temperatures. Instead, you get a narrow twilight zone where conditions fluctuate wildly, where rock cycles between solid, liquid, and gas states in response to turbulent airflow. The geology of such a place would be incomprehensible, erosion patterns carved by winds carrying droplets of molten stone, mountains that melt and reform with each rotation. Some of these lava worlds are tidally locked, always showing the same face to their star. Others rotate, subjecting every point on their surface to cyclical melting and freezing. The thermal stress would fracture any normal planetary crust, creating a surface of constantly shifting plates, volcanic rifts that span hemispheres, convection patterns that make Earth's mantle flow look static by comparison. What's particularly disturbing is how common these planets appear to be. We've found dozens of lava worlds, and we've barely begun surveying nearby star systems. The conditions required aren't that unusual. Put a rocky planet close enough to its star, and physics does the rest. The universe manufactures these hellscapes as readily as it produces normal terrestrial worlds. But extreme heat is only one way matter can be tortured into exotic states. Consider the ice giants that aren't actually ice. Uranus and Neptune in our own solar system hint at this, but exoplanets take the concept to its logical extreme. These worlds have mantles of water, ammonia, and methane compressed into states called superionic ice. In this phase, oxygen atoms lock into a crystalline lattice while hydrogen atoms flow freely between them, conducting electricity like a metal. It's simultaneously solid and liquid, ice that flows, water that conducts. The pressure required to create superionic ice is immense, millions of times Earth's atmospheric pressure. The temperatures are scorching, thousands of degrees, yet the material remains ice by definition because the oxygen lattice stays rigid. This isn't water as we know it. It's a new state of matter that only exists under conditions we can barely replicate in laboratories. Planets with superionic ice mantles would have magnetic fields generated by the flowing hydrogen, similar to how Earth's molten iron core creates our magnetosphere. But the dynamics would be completely different. The convection patterns, the electrical currents, the relationship between rotation and field strength, all operating under physics we're still working to understand. Some models suggest these mantles could be dozens of Earth masses worth of superionic ice, layers so deep that the pressure at the bottom approaches conditions found in stellar cores. At those depths, even our best equations become approximations. We're extrapolating from laboratory experiments conducted with tiny samples held under extreme conditions for microseconds, trying to predict the behavior of planet-sized volumes of matter compressed for billions of years. And we haven't even addressed the magnetic fields these worlds generate. Some exoplanets show evidence of magnetospheres thousands of times stronger than Earth's. The radiation environment around such worlds would be catastrophic. Any moon, any ring system, any spacecraft that ventured too close would be bombarded by particle radiation intense enough to break apart molecular bonds. HD 209458b, one of the first transiting exoplanets ever discovered, is slowly evaporating under its star's radiation. We can actually see the extended atmosphere of escaping hydrogen, a comet-like tail of atmospheric gas being stripped away into space. The planet is losing roughly 600 tons of material every second. At that rate, HD 209458b will survive for billions of years before completely evaporating. But smaller planets in similar orbits don't have that luxury. We found worlds that appear to be the rocky cores of former gas giants, their atmospheres completely stripped away, leaving only the dense interior exposed to space. These stripped cores give us a glimpse of planetary interiors we'd never otherwise see. Layers that should be buried under tens of thousands of kilometers of gas are now surface features. The composition, the structure, the way heat flows through these exposed cores, it's like looking at a dissected planet, one that's been peeled apart by stellar radiation. What remains is often dense beyond imagining. Some of these cores might be primarily iron, compressed to densities approaching that of stellar matter. Others could be rich in exotic materials, carbon compounds, metal oxides, substances that only form under the extreme pressures found deep within giant planets. The more we discover, the clearer it becomes that our categories are inadequate. We talk about gas giants, ice giants, terrestrial planets, trying to impose Earth-based classifications on worlds that laugh at our taxonomies. The universe produces planets we have no names for, compositions we didn't predict, structures that violate our models. And somewhere in that catalog of horrors, there's a realization taking shape. These extreme worlds aren't anomalies. They might be the norm. Earth-like planets, stable orbits, moderate temperatures, those might be the real outliers. We might live on one of the universe's rare gentle worlds, surrounded by a cosmos that specializes in creating nightmares. The question isn't why these extreme planets exist. It's why planets like Earth exist at all. The solar system we grew up studying was a lie. Not intentionally, but a lie nonetheless. We learned about orderly planetary formation, about neat zones where rocky planets form close to the star and gas giants gather farther out, about stable circular orbits that have persisted for billions of years. Then we pointed our telescopes at other stars and discovered that our solar system is the weird one. Planet migration changes everything. Giant planets don't stay where they form. They move, sometimes drifting inward over millions of years, sometimes being violently ejected into the outer darkness. The mechanism is elegant in its brutality. A young planet forming in a disk of gas and dust interacts gravitationally with that material. The disk pushes back. Depending on the planet's mass, the disk's density, and a dozen other factors, the planet either spirals inward toward its star or gets flung outward into exile. Hot Jupiters, those massive worlds orbiting insanely close to their stars, they didn't form there. No gas giant could assemble that close to a star. The radiation would prevent it, blowing away the gas before it could accumulate. Instead, these planets formed farther out, in the cold outer reaches of their systems, then migrated inward, grinding through whatever stood in their way. Imagine what that journey looked like. A Jupiter-mass planet, dozens of times more massive than Earth, slowly spiraling toward its star over the course of 1 million years. Any rocky planets in its path would be gravitationally scattered. Some flung into the star. Others ejected from the system entirely, sent wandering through interstellar space as rogue planets with no sun to orbit. The survivors, the planets that managed to avoid direct collision, would find their orbits completely disrupted, stretched into wild ellipses or tilted at bizarre angles. We found evidence of these disrupted systems everywhere. Planets with orbits tilted relative to their star's equator, sometimes even orbiting backward, counter to the star's rotation. That doesn't happen in a calm, orderly formation process. That requires violence, close encounters, gravitational chaos that reshuffled the entire system. Some migration scenarios are even more dramatic. The NICE model, named after the French city where it was developed, suggests that our own solar system underwent a period of violent upheaval about 4 billion years ago. Jupiter and Saturn, locked in orbital resonance, suddenly broke free. The resulting gravitational chaos sent Neptune careening outward, scattering the primordial Kuiper belt and triggering the late heavy bombardment, a period when the inner solar system was pummeled by asteroids and comets. Earth survived that bombardment. Barely. The Moon's cratered surface is a permanent record of that violent era. If the timing had been slightly different, if Earth had taken a few more direct hits from large impactors, life might never have gained a foothold. We exist because our planet threaded a needle through gravitational chaos. Other systems weren't as fortunate. We found stellar systems with no planets at all in their habitable zones, just hot Jupiters orbiting suicidally close to their stars and maybe a few distant ice worlds in the outer darkness. Whatever terrestrial planets once existed in the temperate middle regions, they're gone, consumed or ejected during the giant planet's inward migration. The Kepler mission revealed something even more unsettling. Compact multi-planet systems, chains of super-Earths orbiting closer to their stars than Mercury orbits our Sun, all locked in tight orbital configurations that shouldn't be stable. Yet they are stable, and they're common. These systems likely formed through migration too, with planets drifting inward and getting trapped in resonant configurations, orbital periods related by simple ratios that keep the planets from colliding despite their proximity. But migration doesn't always lead to stability. Sometimes it leads to ejection. Numerical simulations of young planetary systems show that ejections are common, perhaps inevitable. Most systems probably started with more planets than they currently have. The missing worlds are out there somewhere, drifting through the galaxy as rogue planets, unbound to any star. We've actually started detecting these rogue planets. Not by watching them transit a star, obviously, since they don't have one, but through gravitational microlensing. When a massive object passes in front of a distant star, its gravity bends the starlight, briefly brightening it in a characteristic way. Several of these events have been attributed to planet-mass objects wandering alone through space. How many rogue planets are there? Early estimates suggested there might be more rogue planets in the galaxy than stars. Billions of worlds, maybe trillions, wandering in permanent darkness, their surfaces frozen, any atmospheres long since condensed into ice on the ground. Some of them might still have internal heat, residual warmth from their formation or heat generated by radioactive decay in their cores. Deep beneath their frozen surfaces, there might be liquid water, subsurface oceans kept warm by geothermal energy, completely isolated from any external energy source. Could life exist in such places? It seems absurd, life without sunlight, without a star, on a world that's been adrift for billions of years. But we've found life in Earth's deep ocean trenches, kilometers below the surface, living around hydrothermal vents in complete darkness, deriving all their energy from chemistry rather than photosynthesis. If life can do that on Earth, why not on a rogue planet with a warm core and a subsurface ocean? We'd never find it, of course. Even detecting the rogue planets themselves is extraordinarily difficult. Detecting life on them would be impossible with any technology we currently possess or can realistically envision. But the possibility exists, entire biospheres evolving in the dark, completely unaware that stars exist, that light exists, that there's anything beyond the warm water and rock of their world. Back in systems with stars, migration creates another problem entirely: orbital instability on geological timescales. A planetary system might look stable now, all the planets in neat orbits, no obvious signs of chaos. But run the simulation forward 1 billion years and suddenly planets start crossing orbits, close encounters begin, and the whole system can unravel. Our solar system sits near the edge of that instability. Numerical integrations of the planet's orbits show that while the system is currently stable, there's a small but non-zero probability that Mercury's orbit could become chaotic within the next few billion years. If that happens, Mercury might collide with Venus, or get ejected from the solar system entirely, or worse, its destabilization could trigger a cascade of orbital disruptions affecting the other inner planets. Earth's orbit could change. Not dramatically, not overnight, but over millions of years. The eccentricity could increase, the distance from the Sun could vary more widely between closest and farthest approach, and that would be enough to trigger runaway climate changes that make our current concerns about global warming look trivial. We're living in a temporarily stable configuration. Emphasis on temporarily. On cosmic timescales, stability is an illusion. Every planetary system is slowly evolving, orbits shifting microscopically with each passing millennium, gravitational resonances building and breaking, the whole structure engaged in an endless dance between order and chaos. Some exoplanetary systems show clear evidence of being in the chaotic regime right now. Wildly eccentric orbits, planets crossing each other's paths, configurations that can't possibly last more than a few million years before something collides or gets ejected. We're watching these systems during their death throes, the final stage before the current arrangement destroys itself and whatever survives settles into a new, hopefully more stable configuration. The universe is running a massive experiment in orbital dynamics, testing every possible configuration of planets around every type of star, and we're finally starting to see the results. Most configurations fail. Planets collide, or spiral into their stars, or get ejected into interstellar space. The systems that survive, the ones we see today, they're the lucky ones, the configurations that happen to hit upon something stable enough to last billions of years. And even among the survivors, stability is relative. Given enough time, given billions or tens of billions of years, even the most stable systems will eventually encounter something that disrupts them. A close pass by another star, a rogue planet wandering through, the gradual evolution of the star itself changing the energy balance of the system. Nothing lasts forever. Which brings us to an uncomfortable question. If planetary systems are this fragile, this prone to chaos and disruption, how did Earth manage to remain stable enough for life to evolve? For billion years of relative stability, with only minor variations in orbit, enough consistency for liquid water to persist on the surface, for complex chemistry to develop into biology, for intelligence to eventually emerge. We needed billions of years of boring, predictable orbital mechanics. And apparently, that's rare. Luck alone doesn't explain it. There's structure beneath the apparent randomness, patterns in how planetary systems stabilize over time, and Earth benefited from several of them. Start with Jupiter. Massive, distant, sitting comfortably in the outer solar system where it's been for billions of years. Jupiter acts as a gravitational vacuum cleaner, its enormous mass capturing or deflecting comets and asteroids that would otherwise bombard the inner planets far more frequently. Without Jupiter, Earth would have experienced perhaps 10 to 100 times more impacts over its history. Some of those impacts would have been extinction-level events, resetting the evolutionary clock, wiping out whatever complexity had managed to develop. Life might still exist, but it would be starting over repeatedly, never accumulating the billions of years of uninterrupted evolution needed to produce anything as complex as multicellular organisms, let alone intelligence. Jupiter's position matters too. If Jupiter were closer, its gravitational influence would destabilize Earth's orbit. If it were farther out, it wouldn't provide as much protection from incoming debris. The current configuration represents a narrow window where Jupiter helps more than it harms. And we got lucky. Or did we? The nice model suggests that the giant planets didn't form where they are now. Early in the solar system's history, Jupiter, Saturn, Uranus, and Neptune were in different orbits, probably closer together, and their gravitational interactions with the remaining planetesimals, the leftover building blocks of planet formation, caused them to migrate. Jupiter moved inward slightly before being pushed back out by Saturn. The ice giants, Uranus and Neptune, scattered outward, clearing the outer solar system and creating the Kuiper belt in the process. This migration phase was chaotic, violent, a period when the solar system was reorganizing itself into something more stable. And somehow, during all that upheaval, Earth's orbit remained relatively untouched. The migration happened early enough that the terrestrial planets were already formed and massive enough to resist being swept away by the gravitational chaos, but late enough that the giant planets could settle into orbits that would protect rather than destroy the inner system. Timing mattered. A few million years difference in when the migration occurred and Earth might not exist, or it might have ended up with an orbit so eccentric that surface temperatures swing between boiling and freezing every few thousand years. Instead, we got stability. Boring, predictable stability that lasted long enough for chemistry to become biology. But even with Jupiter in the right place, even with the migration happening at the right time, Earth still needed one more thing. The Moon. Earth's moon is absurdly large compared to the planet it orbits. Most moons in the solar system are tiny compared to their host planets, captured asteroids, or leftover debris from planetary formation. Earth's moon represents about 1% of Earth's mass, a ratio that's huge by solar system standards. And that mass, that proximity, stabilizes Earth's axial tilt. Without the moon, Earth's axis would wobble chaotically over timescales of tens of thousands to millions of years. The tilt, currently around 23.5 degrees, determines the severity of seasons. A larger tilt means more extreme seasons, hotter summers and colder winters. A smaller tilt means milder seasons but also changes where and how much sunlight different parts of the planet receive throughout the year. If Earth's tilt varied chaotically, climate would vary chaotically. Ice ages would come and go unpredictably, ocean currents would shift, weather patterns would destabilize, and any ecosystem trying to adapt to one set of conditions would be blindsided when those conditions changed radically a few 100,000 years later. The Moon's gravitational pull acts like a gyroscopic stabilizer, keeping Earth's axis locked within a narrow range of variation. Mars offers a cautionary comparison. Mars has two tiny moons, Phobos and Deimos, captured asteroids with negligible gravitational influence on the planet's orientation. As a result, Mars's axial tilt varies wildly over millions of years, swinging between 10 and 60 degrees. When the tilt is high, the poles receive direct sunlight, ice caps sublimate, the atmosphere thickens temporarily, and the climate shifts into a completely different regime. Then the tilt decreases, the poles freeze again, the atmosphere collapses back down, and the climate returns to its current thin, cold state. Any life trying to establish itself on Mars would face these massive climate swings, environments that change so drastically that adaptation becomes nearly impossible. Earth avoided this fate because a Mars-sized object, often called Theia, slammed into the early Earth around 4.5 billion years ago. The collision was so violent that both bodies were partially vaporized, and the debris from the impact coalesced into the moon. This wasn't gentle. This was a planet-scale catastrophe that reset Earth's formation, melted the surface, ejected enormous amounts of material into orbit. But the end result was a moon large enough and close enough to stabilize Earth's rotation for billions of years. Pure chance. If Theia had hit at a slightly different angle, or with a different velocity, the debris might not have formed a moon at all. Or it might have formed multiple smaller moons that eventually collided and destroyed each other. Or the collision might have been so violent that Earth itself was shattered beyond recovery. Instead, we got exactly the right impact, at exactly the right time, producing exactly the right outcome. It's almost suspicious how well everything lined up. Which brings up the anthropic principle. The idea that we observe the conditions we do because those are the only conditions under which observers like us could exist. In a universe with billions of galaxies, each containing billions of stars, each potentially hosting multiple planets, the vast majority of those planets will have chaotic orbits, or no moons, or giant planets in the wrong positions, or any number of other configurations that make long-term stability impossible. But we're not on those planets. We can't be. We can only exist on a planet where everything happened to work out, where the orbital mechanics were stable enough, where the impacts happened at the right time, where the moon formed and Jupiter migrated and the axial tilt stabilized. From our perspective, it looks like an incredible string of coincidences. But it's only incredible if you ignore the countless other planetary systems where things didn't work out. The ones with no observers, no one around to notice how unstable and inhospitable they are. We're sampling from a biased dataset. Every civilization that ever asks, "Why is our planet so stable?" is asking from a planet that happened to be stable, because instability doesn't produce civilizations capable of asking questions. So maybe Earth's stability isn't rare in an absolute sense. Maybe it's just rare among the subset of planets we're capable of observing from the inside. Except we can now observe other planetary systems. And the data suggests that configurations like ours genuinely are uncommon. Most systems don't have a Jupiter analog sitting in the right orbit. Most don't have a large stabilizing moon. Most show signs of past migration events that disrupted everything rather than settling into stable configurations. The Kepler mission, which surveyed over 500,000 stars looking for transiting exoplanets, found thousands of planetary systems. And the vast majority look nothing like ours. Hot Jupiters orbiting closer to their stars than Mercury orbits the Sun. Super-Earths in tight orbits with year-lengths measured in days. Systems with multiple planets crammed into the space where Mercury's orbit would be. Compact, tightly packed configurations that probably formed through violent migration and scattering events. Our solar system, with its well-spaced planets, its giant planets in the outer system, its small rocky planets closer in, appears to be in the minority. Not impossible, clearly, since we exist. But not the default outcome of planet formation either. Which raises the question of what the default outcome actually produces. If most planetary systems end up chaotic, with unstable orbits and frequent catastrophic events, does that mean life is correspondingly rare? Or does life find a way to adapt even to chaotic conditions? Maybe civilizations arise on planets with wildly varying climates, where evolutionary pressure is so intense that intelligence develops faster because survival demands it. Maybe we're the weird ones, living on an unusually stable planet that allowed life to take its time, to evolve slowly without constant existential threats forcing rapid adaptation. There's no way to know yet. We've only found one example of life in the universe, and it's us. We're trying to extrapolate from a sample size of one, trying to figure out whether Earth's stability was necessary for our existence or just one path among many. The discovery of life elsewhere, especially complex life, would answer that question immediately. If we find it on a planet with a chaotic orbit, or no moon, or a close-orbiting giant planet, then stability wasn't necessary after all. Life is more robust than we thought, capable of thriving under conditions we assumed were prohibitive. But if we search 1,000 nearby stars, examine 1,000 planetary systems, and find nothing, no biosignatures, no signs of even simple microbial life, then maybe Earth's stability really was essential. Maybe the combination of factors that allowed life to develop here is so specific, so unlikely, that we're alone in the galaxy despite the billions of planets available. Neither answer is comforting. Finding life elsewhere would tell us we're part of a common pattern. Finding nothing would tell us we're the result of a cosmic lottery that almost never pays out. And we'd still be stuck here, on this one stable planet, wondering what we're supposed to do with that information. But stability itself might be temporary. Even Earth, with all its protective mechanisms, all its fortunate accidents, isn't locked into its current state forever. The moon is slowly drifting away. Not quickly. About 3.8 centimeters per year, roughly the rate your fingernails grow. Over human timescales, irrelevant. Over geological timescales, significant. In the deep past, the moon was much closer. Days were shorter, tides were stronger, the moon appeared enormous in the sky. As it recedes, Earth's rotation slows, days lengthen, and the stabilizing influence weakens. Billions of years from now, if nothing else interferes, Earth's axial tilt will start to wander again, seasons will become unpredictable, and the climate stability that allowed complex life to flourish will erode. Not a catastrophic collapse, but a slow drift back toward chaos. Jupiter won't protect us forever either. Orbital mechanics are deterministic over short timescales but chaotic over long ones. Tiny gravitational perturbations accumulate. Resonances shift. What's stable now might not be stable in a billion years. Models suggest that the solar system's current configuration is probably stable for another few billion years, but probably isn't the same as certainly. There's a non-zero chance that planetary orbits could become unstable, that resonances could shift in ways that send objects careening through the inner solar system. Mercury's orbit, in particular, shows signs of potential long-term instability. Some models predict it could be ejected from the solar system entirely, or collide with Venus, or even fall into the Sun. Low probability, but not impossible. And then there's the Sun itself. Main sequence stars aren't static. They brighten over time as hydrogen fusion in the core gradually increases in efficiency. The Sun today is about 30% brighter than it was when Earth formed. In another billion years, it'll be bright enough that Earth's oceans will begin to evaporate. The resulting water vapor will amplify the greenhouse effect, triggering runaway warming. Earth will become Venus, a scorched world with a crushing atmosphere and surface temperatures hot enough to melt lead. Complex life will be impossible long before that. Possibly within a few 100 million years, the conditions that allowed us to exist will have shifted beyond habitability. Earth's stability has an expiration date, which means the window during which Earth can support technological civilizations is narrower than the total lifespan of the planet. Earth existed for 4 billion years before humans appeared. It'll exist for another 5 billion before the Sun expands into a red giant and consumes it entirely. But the period during which conditions are right for civilizations like ours? Maybe 1 billion years total. Possibly less. We arrived relatively early in that window, cosmically speaking. If intelligent life had taken another billion years to evolve, it might have missed the opportunity entirely. The planet would already be too hot, the oceans gone, the climate spiraling into uninhabitability. That timing raises uncomfortable questions about how much longer the window stays open. If Earth remains habitable for another few 100 million years, that's plenty of time for other intelligent species to evolve after we're gone. But if the window is closing sooner, if climate instability or solar brightening starts to make complex life untenable within the next 100 million years, then we might be the only species that gets a chance. The first and the last, arriving at the only moment when conditions align properly. Some researchers argue that we're already seeing the early stages of that closing window. Earth's climate has been unusually stable for the past 10,000 years, the entire span of human civilization. Before that, during the Pleistocene, ice ages came and went with regularity, driven by small variations in Earth's orbit and axial tilt. The current interglacial period, the Holocene, has lasted longer than most. Long enough for agriculture to develop, for cities to rise, for technology to advance to the point where we can ask these questions. If the ice had returned a few thousand years earlier, human civilization might never have formed. We'd still be scattered hunter-gatherer tribes, surviving but not building. The stability of the Holocene might itself be an anomaly. A brief moment of calm between longer periods of chaos. If that's true, then our existence depends not just on Earth's long-term stability relative to other planets, but on a short-term stability relative to Earth's own history. We didn't just need a stable planet. We needed a stable decade within a stable millennium within a stable epoch. Layer after layer of coincidence, each one necessary but not sufficient. And human activity is now destabilizing the climate in ways that could end that window prematurely. We're releasing carbon dioxide at rates not seen since the asteroid impact that killed the dinosaurs. We're altering atmospheric composition faster than natural processes can respond. If we push the climate past certain tipping points, runaway feedback loops, melting permafrost releasing methane, collapsing ice sheets changing ocean circulation, Earth could shift into a new state. Not uninhabitable necessarily, but different enough that the civilization we've built can't survive the transition. We'd lose the stability that allowed us to exist in the first place, not because of cosmic bad luck, but because we didn't recognize how fragile the balance was. That's the paradox. Earth's stability is both robust and fragile. Robust enough to survive billions of years of asteroid impacts, volcanic eruptions, ice ages, and mass extinctions. Fragile enough that small changes in atmospheric composition or orbital parameters can shift it into entirely different regimes. The Moon stabilizes the tilt, but only within limits. Jupiter clears the inner system, but only probabilistically. The Sun provides steady energy, but only for a finite period. Every protective mechanism has boundaries. Push past them, and the system doesn't just wobble. It transforms. We're living in the narrow zone where all those mechanisms are working simultaneously. The Moon is close enough to matter, but not so close it tears us apart. Jupiter is far enough to avoid disrupting our orbit, but close enough to clear out threats. The Sun is bright enough to keep the planet warm, but not so bright it boils the oceans. Atmospheric composition is balanced between greenhouse warming and runaway freezing. Each variable has a range, and we're sitting near the center of all of them at once. Not at the exact center, there's no such thing, but within the habitable band for each factor. The probability of that happening by chance is low. Not impossible, because here we are. But low enough that finding another planet with the same combination of factors would be surprising. Which brings us back to the central question. Are we alone because stable planets are rare? Or are we alone because the transition from simple life to complex intelligent life is the real bottleneck, and planetary stability is just one of many requirements? If we found 1,000 Earth-like planets, how many would have life? How many would have intelligent life? How many would have civilizations capable of asking these same questions? We don't know. We're still searching. Exoplanet surveys are finding more potentially habitable worlds every year. Planets in the habitable zone of their stars. Planets with atmospheres. Planets with water. But none confirmed to have life yet. No radio signals. No chemical biosignatures. No signs that anyone else is out there asking the same questions we are. Maybe we're looking in the wrong places. Maybe life is common but intelligent life is rare. Maybe intelligence is common but technological civilizations are short-lived, appearing briefly and then destroying themselves before they can be detected. Maybe we're early, the first civilization to emerge in a galaxy that will eventually be crowded with life. Or maybe we're exactly what the statistics predict. The unlikely outcome of an unlikely process on an unlikely planet. A single experiment that succeeded once and might never succeed again. Earth's stability gave life a chance, and life took 4 billion years to produce something capable of understanding that stability. That's a long time. Long enough that if the process had been interrupted at any point, by a slightly larger asteroid, a slightly closer supernova, a slightly different orbital resonance, we wouldn't be here. And no one would be around to notice the difference. That's the uncomfortable truth sitting underneath all of this. Earth's stability isn't guaranteed. It's contingent. Dependent on factors that could have been different, that might become different, that are already changing in ways we don't fully control. The moon will drift away. The sun will brighten. Jupiter's orbit will shift. And eventually, the conditions that allowed us to exist will disappear, replaced by something harsher, less forgiving. The question isn't whether Earth will remain stable forever. It won't. The question is how much time we have left, and what we do with it. Because if this really is the only stable planet capable of supporting intelligent life within a radius of hundreds or thousands of light years, then what happens here matters in ways we're only beginning to understand. Earth's long-term stability isn't theoretical. It's measurable, trackable, and already changing in real time. The same gravitational forces that kept the planet habitable for billions of years are still in motion, but the balance is shifting. Not catastrophically, not suddenly, but persistently. And persistence, over geological timescales, is what reshapes worlds. The moon is receding from Earth at roughly 3.8 centimeters per year. That sounds negligible. It is negligible, on human timescales. But over hundreds of millions of years, that small drift accumulates into something much larger. The moon was once closer, which means Earth's day was shorter, its tides were stronger, and its axial tilt was stabilized more aggressively. As the moon moves away, that stabilization weakens. The tilt becomes more vulnerable to perturbations from other planets, particularly Jupiter and Venus. More variation in tilt means more extreme climate swings. Ice ages become deeper. Warm periods become hotter. The transitions between them become sharper, harder for ecosystems to navigate. Right now, Earth's axial tilt varies by about 1 degree over a cycle of roughly 41,000 years. That's enough to drive glacial and interglacial periods, but it's not enough to destabilize the climate entirely. Mars, without a large stabilizing moon, has an axial tilt that varies by tens of degrees over similar timescales. Sometimes it's nearly upright. Sometimes it's tilted so far that its poles face the sun directly. That kind of variation would be catastrophic for complex life. Earth avoided that fate because the moon exists and because it's large enough to matter. But it won't always be large enough. Eventually, the gravitational coupling will weaken to the point where other forces dominate, and the stability we've relied on will erode. The Sun is also changing. Not rapidly, but inevitably. Main sequence stars like the Sun gradually increase in luminosity as they age. Over the past 4 billion years, the Sun has brightened by roughly 30%. That might not sound like much, but it's enough that early Earth, with the same atmosphere we have today, would have been frozen solid. It wasn't, because the atmosphere was different. Thicker with greenhouse gases, trapping more heat, compensating for the dimmer Sun. As the Sun brightened, the atmosphere thinned, and the balance shifted. But that balance only works within a narrow range. The Sun will continue brightening, and eventually, no amount of atmospheric adjustment will keep Earth habitable. Models suggest that in roughly 1 billion years, the oceans will begin to evaporate. Not all at once, but steadily, as increased solar radiation breaks water molecules apart and hydrogen escapes into space. Once the oceans are gone, the planet becomes Venus. Hot, dry, lifeless. Jupiter's orbit is also shifting, though far more slowly. The gas giant doesn't stay in a perfectly stable position. Gravitational interactions with Saturn and the other outer planets cause Jupiter's orbit to oscillate slightly over millions of years. Those oscillations affect the asteroid belt, periodically destabilizing certain regions and sending more debris toward the inner solar system. That's one reason why asteroid impacts on Earth haven't been evenly distributed over time. There are periods of increased bombardment, driven by orbital resonances in the outer solar system. We're currently in a relatively quiet phase, but that won't last forever. The next resonance could send a new wave of asteroids inward, and one of them could hit Earth. Not guaranteed, but possible. And over long enough timescales, possible becomes probable. Plate tectonics, the process that recycles carbon and regulates the planet's temperature, is also slowing. The Earth's interior is cooling. Not quickly, but measurably. As it cools, mantle convection weakens, and the plates move more slowly. Eventually, they'll stop moving altogether. When that happens, the carbon cycle breaks. Volcanoes stop erupting. Carbon dioxide stops being released into the atmosphere. Weathering continues, pulling CO2 out of the air and locking it into rock, but there's no mechanism to put it back. Atmospheric CO2 drops, temperatures fall, and the planet enters a permanent ice age. That's billions of years away, but it's coming. The same process that kept Earth habitable for 4 billion years has an expiration date, and there's nothing we can do to extend it. So if Earth's stability is temporary, and if the conditions that allowed life to thrive are already beginning to change, what does that mean for the search for other habitable worlds? It means we need to stop thinking about habitability as a binary condition. A planet isn't simply habitable or not habitable. It's habitable for a certain period, under certain conditions, with certain margins of error. Earth has been continuously habitable for billions of years, but that's the exception, not the rule. Most planets, even if they start out habitable, probably don't stay that way for long. They lose their atmospheres, or their orbits destabilize, or their magnetic fields collapse, or their stars brighten too quickly. The window of habitability closes, and whatever life existed either dies out or never advances beyond simple microbial forms. That's why finding another Earth is harder than it sounds. It's not enough to find a rocky planet in the habitable zone. It needs to have the right size, the right atmosphere, the right orbital stability, the right magnetic field, the right amount of water, and the right geological activity. And it needs to maintain all of those conditions for billions of years, long enough for complex life to evolve. That's an extraordinarily narrow target. We've found thousands of exoplanets, and a handful of them are in the habitable zone, but we don't know if any of them meet all the other criteria. We can measure their size and their distance from their star, but we can't measure their axial stability, their magnetic field strength, or their tectonic activity. Not yet. Maybe not for decades. And even if we do find a planet that checks every box, that still doesn't tell us whether life actually exists there. Because habitability is necessary, but it's not sufficient. Life also needs to start, and we still don't fully understand how that happens. We know it happened on Earth, but we don't know if it was likely or unlikely. We don't know if it requires specific chemical conditions, specific energy sources, specific environmental niches. We don't know if it happens quickly, within the first few 100 million years of a planet's existence, or if it takes longer. We don't know if it happens once and then spreads, or if it happens multiple times independently. All of that is still unknown, which makes it impossible to estimate how common life is in the universe. What we do know is that even if life is common, intelligent life is probably rare. It took 4 billion years for Earth to produce a species capable of building telescopes and asking these questions. 4 billion years of evolution, mass extinctions, environmental upheavals, and random chance. If any one of those mass extinctions had been slightly more severe, if the asteroid that killed the dinosaurs had been slightly larger or struck at a slightly different angle, if oxygen levels had never risen high enough to support complex organisms, we wouldn't be here. Intelligence isn't an inevitable outcome of evolution. It's one possible outcome, and it required an enormous amount of time and an extraordinary amount of luck. So when we look out at the universe and see no signs of anyone else, that might not mean we're alone. It might just mean that intelligent life is vanishingly rare, appearing briefly on a tiny fraction of habitable planets before disappearing again. Or it might mean that intelligent civilizations don't last long enough to be detected. They emerge, they develop technology, and then they destroy themselves, or their planets become uninhabitable, or they simply lose interest in broadcasting their presence. We don't know. We're still at the beginning of the search, and we've barely started looking. But here's what we do know. Earth gave us a chance. A stable platform, a long stretch of time, and conditions that allowed complexity to emerge. That chance won't last forever, and it might not exist anywhere else within reach. Which means that what we do here, in the brief window we have, matters more than we usually think about. Not in some abstract cosmic sense, but in a very practical one. If this really is the only place where intelligence has emerged, if this really is the only planet capable of asking these questions and searching for answers, then letting it slip away would be the ultimate waste. We're not at the center of the universe. We're not special in any cosmic sense. But we might be the only ones around who can understand what it took to get here, and what it would mean to lose it. That's not a reason to panic, but it's a reason to pay attention. Because stability isn't guaranteed, time isn't infinite, and the conditions that made all of this possible are already changing. The question is whether we notice before it's too late. The catalog of extreme worlds we've surveyed, from glass rain planets to diamond spheres, from lava oceans to rogue worlds wandering in permanent darkness, these aren't just cosmic curiosities. They're data points in the largest experiment ever conducted. An experiment with no control group, no hypothesis, just billions of planetary systems testing every possible configuration to see what survives. And what survives, mostly, is chaos. Orbits that decay. Atmospheres that boil away. Planets that migrate inward and destroy everything in their path. The default outcome of planet formation appears to be instability, not the orderly solar system we grew up learning about in textbooks. Earth sits somewhere in the statistical tail of that distribution. Not impossible, clearly we exist, but uncommon enough that finding another planet with the same combination of protective factors would be genuinely surprising. The right-sized moon in the right orbit. A gas giant positioned to clear debris without disrupting inner planets. An axial tilt that stays within bounds. Plate tectonics that regulate temperature. An atmosphere that maintains itself for billions of years. Each factor individually might be common. All of them together, persisting simultaneously for geological timescales, that's where the probability drops. But rarity doesn't mean uniqueness. In a galaxy with hundreds of billions of stars, even a 1 in a million chance produces hundreds of thousands of candidates. The question isn't whether other stable planets exist. Statistically, they must. The question is whether we'll ever find them, whether they're close enough to detect, and whether they happen to produce something capable of being detected. Because stability alone doesn't guarantee intelligence. Earth was stable for 4 billion years before anything resembling human civilization appeared. 4 billion years of microbial life, simple multicellular organisms, evolutionary dead ends and fresh starts. Intelligence emerged once, recently, and it required nearly the entire span of Earth's habitable period to do so. If we're typical, then most stable planets are probably inhabited by microbes, maybe simple animals, but nothing that builds radio telescopes or wonders about its place in the cosmos. And if intelligence does emerge, there's no guarantee it survives long enough to matter. Civilizations might be brief, appearing for a few thousand years before destroying themselves or being destroyed by their own success. We're learning this in real time, watching our own civilization strain against the limits of the planet that produced it, altering atmospheric composition faster than natural systems can respond, destabilizing the very climate stability that allowed us to exist. The extreme planets aren't warnings. They're not cautionary tales about what happens when things go wrong. They're just physics playing out in environments where the initial conditions were different. But they do illustrate something important. Small changes in planetary parameters produce massive differences in outcomes. A slightly closer orbit and you get a lava world. A slightly more eccentric orbit and you get temperature swings that prevent complex chemistry. A slightly different stellar neighborhood and you get bombarded by radiation until your atmosphere strips away. Earth avoided all of those failure modes. Not through any special protection, but through a combination of initial conditions and subsequent events that happen to fall within the narrow band where stability persists. We're not special. We're lucky. And luck, by definition, runs out. The moon is drifting away. The sun is brightening. The planet's internal heat is dissipating. Every mechanism that kept Earth habitable has a timer attached, and some of those timers are already approaching zero. Not tomorrow, not next year, but on timescales that matter if you're thinking about the long-term future of life in the universe. Which means the window we're in, this brief period where Earth is stable enough to support technological civilization, might be closing sooner than we'd like to think. Not millions of years from now. Possibly within hundreds of thousands of years, maybe less if we accelerate the closing through our own actions. The Holocene, this unusually stable climatic period that allowed human civilization to develop, has already lasted longer than most interglacial periods. The next ice age could begin tomorrow in geological terms, while we could push the climate so far in the other direction that we trigger feedbacks that make the planet uninhabitable for anything resembling current life. Either way, we're living in a temporary condition. A moment of calm between longer periods of chaos. And we're only just now developing the tools to recognize that, to understand the mechanisms that created this calm and the forces that will eventually end it. The extreme planets force us to confront that reality. They show us what happens when any one of Earth's protective factors is missing or degraded. They demonstrate that habitability isn't a stable attractor state. It's a temporary condition that requires continuous maintenance through geological and astronomical processes we don't control and can barely influence. So when we look at HD 189733b with its glass rain and supersonic winds, or KLT 9b being vaporized by its own heat, or the rogue planets wandering alone through interstellar space, we're not looking at alien hells. We're looking at alternate versions of what Earth could have been, or might become, if the initial conditions had been slightly different or if the mechanisms preserving stability fail. That's the real message hidden in the catalog of extreme worlds. Not that Earth is special, but that it's fragile. That the conditions we take for granted, the stable orbit, the protective moon, the active geology, none of those are permanent features. They're temporary states maintained by processes that are themselves slowly changing. And when those processes shift beyond certain thresholds, the planet shifts with them, potentially into states where intelligence can no longer exist. We're still searching for other Earths, other stable platforms where life might have had the same chance we did. And we'll keep searching, because the alternative, accepting that we might be alone, is harder to process than the idea that we just haven't looked carefully enough yet. But with each new extreme planet we discover, with each new configuration that turns out to be hostile to life, the statistical space where other civilizations could exist shrinks slightly. Maybe we'll find them. Maybe there are other stable worlds with their own observers, asking the same questions, wondering if they're alone. Maybe the galaxy is full of intelligence and we're just not looking in the right way or at the right frequencies. Or maybe the extreme planets are showing us the universe's default setting. Chaos, instability, conditions that prevent complexity from accumulating over the billions of years required to produce anything interesting. And Earth, stable boring Earth with its regular orbit and its protective moon and its steady sun, is the outlier. The statistical anomaly. The place where everything happened to line up just right for just long enough. We won't know until we keep looking. But every extreme planet we find, every world that's too hot or too cold or too chaotic or too unstable, narrows the space where we might find company. And if that space continues to narrow, if we search 1,000 stars and find nothing, then we're left with an uncomfortable conclusion. That this might be it. This might be the only place in our corner of the galaxy where the universe briefly organized itself into something capable of understanding what it is and where it came from. And that understanding came with a responsibility we're only beginning to recognize. To not waste the chance we were given, however unlikely it was.